Hi, my name is Korbinian Niebler and I want to welcome you to this presentation I've given at the 2025 SoTiC conference in Trondheim, Norway. NTNU Aero Engines has suggested a novel concept where steam, so water vapor, is injected into the gas turbine process or actually also into combustion process as an additional thermal load. With that, they are highly interested in how does that actually influence the thermoacoustic behavior or the flame dynamics of such a wet flame configuration. In a second step, they are also highly interested in how actually those flames thermoacoustically scale. In order to study this, we select a flame configuration that has been well studied over the past years, which is the one of a laminar premixed methane air flame. If we think about those types of flames, we usually have in mind the conical or V flames on the one hand side, studied for example by Thierry Schuller and his group, and on the other hand side, slit flames that have been tackled in Thomas Steinbacher's work. Thierry Schuller suggesting the convective perturbation velocity model and Steinbacher using a flame-based displacement model, both using however a level Sept, so a G equation approach, they agree on one significant thing. They say that the flame response of such flames is governed by two time scales or two time delays actually. However, if we have a look at our wet flames, which are due to that additional thermal load quite long, we see that we have a clear deviation from the shape of the FIR that we would have expected for laminar slit flames, and we have laminar slit flames in our case. We do see that we have tau 1 and tau 2 corresponding to the global maximum and the global minimum, so we can characterize them as well for our case. But before tau 1, we have a clear indentation in the slope of the FIR here. So, how can we investigate this effect? We first use in detail CFD simulation to characterize the reactive flow physics and lift basically those effects, those governing reactive flow physics from the background into the light to see their effect on the flame response here. We then are able to model the flame response given some physical knowledge from our reactive flow physics. So in order to have a parameter space, a model parameter space, which will be available for scaling. By a first principle approach, we then find the physical quantities that play a major role in the scaling behavior of such flames, especially of course if we talk about the scaling of the time delays in our case, which will be the last step of this study. We want to characterize the phenomena of the reactive flow as separately as possible, and this is why we built an extensive testing matrix where we have the water to gas ratio explained at the bottom of the slide, the inlet velocity and the equivalence ratio phi as our three independent control parameters. This means we end up with a matrix where always two parameters are being kept constant here on the left, and we vary in the cases over the steam content. With a well-established routine of CFD coupled with tools from system identification, we get or obtain from reference velocity measurements and global heat release rate measurements. We capture the flame response for all of the cases in terms of the FIR, the finite impulse response, and in terms of the FTFs, so the flame transfer function. If we have a look at the impulse responses of the last row, so basically of constant flame thickness and inlet velocity, we see that with increasing flame length, that this separation of time scales or the emergence of this third time delay becomes more and more prominent here. So in order to study what is going on behind that, we need to really emulate this impulse response by actually forcing the system with an impulse velocity signal at the inlet. If we have a look at that, and you should know this plot also from Wolfgang's plenary talk, we can track basically the deviation of heat release compared to the unperturbed state, where red means an increase and blue, of course, a decrease in the local heat release. What we see with this plot is that as soon as the impulse hits the flame gets elongated, given the red color, so after the flame. And right after that, there follows a process where the flame is not even set back to its unperturbed shape, but set back further, basically, which we will call in this presentation an over-restorative process or over-restoration. So we see that this elongation process is counteracted by this over-restorative process, where both of them travel from the flame base to the flame tip. If you relate this to the impulse response in time domain, we can clearly show that number 2, corresponding here to the global maximum, is the point where this elongation process kind of agglomerates here at the tip, and we have the maximum elongation of the flame at the tip. Correspondingly, at point 3 in time, so this corresponds to the global minimum in the FIR, we see that this over-restorative process actually arrives at this point in time at the tip. So we have the maximum over-restoration at the tip. The question remains, however, what does this number 1 correspond to, or what does it stand for? And this is the exact moment in time we see when this over-restorative process starts its travel basically at the flame base. With that, what we can conclude is, of course, that there are actually 3 time delays needed to characterize the flame response of such long flames. So not only 2, but 3 actually now. We want to further validate this by modeling the flame response in terms of distributed time delays, so by Gaussian terms basically. We use a custom optimization algorithm in order to adapt those Gaussian terms to our flame response, and note that this algorithm is physics constrained. By comparing the model fits for 3 Gaussian terms, 3G, and 2 Gaussian terms, a 2G model, we can directly infer the superiority in terms of the accuracy of the 3G model. Here, for the FTF and frequency domain, we see that the 2G model struggles to capture the phase behavior at higher frequencies. It is also not able to capture those modulations near the cutoff frequency, and also the peak of the gain, so the axis gain, especially the location, cannot be captured correctly here. In time domain, this is quite similar. So we see that this indentation, this pronounced third time delay, can only be captured by our 3G model, as well as the location and the peak height, the amplitude of the global maximum of the FIR. With that plot, we also show the contributions of the individual Gaussian terms. And note that this is quite important, I think, that not necessarily actually the global or the maximum of the individual Gaussian terms does fall together with the maximum or the troughs or the minimums of the impulse response. That is, of course, due to superposition of these terms. Superposition is also the reason when we compare 2G and 3G model that we see that the peak location, amplitude, and the width, so the standard deviation of the Gaussians, do not correspond between 3G and 2G model. Especially for that, have a look at the green, so the third Gaussian term that is included in the model here, the green one. This is especially critical if we talk about the scaling of those model parameters. As we see, for 2G and 3G, they do not really correspond. However, when we really have a look at the scaling of those model parameters over the 4 cases of constant flame thickness, what we rather see is that both actually for 2G and 3G model, the model parameters scale very similarly. We see that the ends are hardly affected actually by our flame length. The sigmas show a tendency of increasing with flame lengths, but clearly most prominent are the taus, which have a clear dependence on the flame lengths, and this is why we will focus on those for the 3G model, on the taus for the 3G model for the remainder of this presentation. In order to find a scaling rule for them, we have to characterize the parameters that govern that have an influence here on the scaling of those time delays. And for that, we basically apply the ansatz of first principles, find those physical quantities and reduce them and boil them down to a space of non-dimensional pi groups, which might play a role in the dynamics for those time lags basically. We find a set of 6 non-dimensional pi groups. However, with a strict focus on the time lags of the flame response, we can neglect or further boil down this parameter space. First, we can assume geometrical similarity. The geometry stays unaltered and the flame shape stays roughly the same, so we can neglect pi 2 and pi 1. By saying, the viscosity will probably not play a big role, we can also neglect pi 6 here. And with the strict description of the flame as a kinematic flame sheet, we can also neglect chemical parameters, so we end up with pi 4 describing the convective transport across or along the flame sheet, which is in our case characterized by the inverse of a Struhal number. This is the exact result we would have obtained by using the G equation approach with the uniform velocity model. We can now use this simple approach of using one Struhal number only to scale the impulse responses of our system. With that, we see that now basically the envelopes of it seems that the envelopes of the FIRs kind of fall together. Not really the physical effects, but rather the envelopes. So what does it actually mean for our individual time delays? And for that, we have to first take into account, or we will take into account, all of the 20 cases to have a more robust scaling behavior. You see the variation of parameters in the top of the slide here. Also, for that, we define a convective timescale tau c here, for which we can relate all the time delays in the end to. So this tau c, if we plot our taus over tau c, that we see that they quite well already scale with our newly defined convective timescale. Especially tau 2 agrees well to our suggested scaling here. We have some outliers at lower tau c, so lower convective times, which means really short flames, and I can tell you the flames we had a look here were quite planar as well, and that means that the assumption before made of geometrical similarity cannot be kept for those flames. That's what we suspect here. One thing is striking, that we have found at tau c that our tau 2, so this corresponds here to the global maximum in the FIR, is basically defined by our tau c. And having a look at the definition of our tau c, which is kind of a convection time from the leading edge of the slit until the tip of the flame, we see that the tau 2 directly corresponds to that. This means tau 2 describes a convective process governing the distance from the leading edge of the slit towards the flame tip. And following the explanations of Philip Brokoff et al., we assume that vorticity shed from the leading edge of the slit might play a big role here. We can confirm that by actually plotting the vorticity in our CFD simulation that has been hit with a velocity input in the form of an impulse. So we compare the scaling now of the three effects or of the three time delays separately to the one where we scale the impulse response by just one Struhal number. And we see now that not the envelopes fall together, but rather the actual physical effects, the three physical effects characterized by our three Gaussian terms, by our three time delays, they now really scale and they fall together. We have thus found that to characterize the flame dynamics of such long flames, it is quite necessary to take into account three time delays. All of those three time delays scale with a convective time delay, which is defined, or with a convective time scale, which is defined from the leading edge of the slit towards the flame tip. We've also kind of found the physical reasoning behind tau 2, which corresponds to the maximum in the FIR, and we assume that vorticity shed from the leading edge traveling to the tip plays a huge role in the flame dynamics of such slit flames here. Thank you.